My name is Tejas Ranade, and I'm going to talk about offline and persistence in mobile apps. And we'll explore the landscape, we'll explore why it matters, why we as mobile developers should care. And I have a few examples that I've worked on that might be interesting to this group. So to start off, I've been a mobile and web developer for a few years now. I started working on mobile apps soon after the iOS was first released, which seems like a long time ago now. But I was a native iOS developer for a long period of time. I worked on native Android for a bit. Most recently, I've been working for Kinvey. Kinvey is a serverless cloud platform that allows businesses to build secure and support apps. And that sounds like a lot of words. It helps to think of Kinvey in the same sense as products like Firebase or Parse. At Kinvey, we provide a set of backend services that all apps need. Things like data storage, user management, serverless functions, scaling and hosting and things like that. And on the front end for your apps, we provide a set of SDKs, and we support all of the platforms that you would typically use to build web and mobile apps. So we have SDKs for iOS and Android, things like Xamarin, all of the JavaScript frameworks that work on mobile and web. So that's where I come from. And what we're going to talk about today is offline. And I thought I'll start off by showing you something that should scare every mobile developer. It's Halloween week after all. So this freaks me out. Hopefully it freaks you out as well. Because if your apps do this, your users are gone. And for the next 30 minutes or so, let's talk about some ways to make this experience better, some ways to solve for problems like this, network errors and loading spinners, and try to figure out what are some techniques we can use to get rid of the dreaded loading indicators. So a little bit of a history lesson. I call these the early days. It probably means I'm getting old, but back in sort of late 2008, 9, or early 2010s, this was sort of the status quo, right? Networks were pretty bad. And weren't really catching up with the speed of how people were developing and releasing apps. So pretty much every app you used would have extended periods of waiting. And over time, a lot of these things have gotten better. Phones have gotten faster. Networks have gotten drastically better. Wi-Fi is much more permeant. But I looked at apps today, and this is a screen capture from my wife's phone as of yesterday. She uses a Pixel. And if you look at this, all of these apps are using enormous amount of space on disk, which means they're still storing a lot of data to be used when networks are not available. And this kind of proves that this is not something that was a temporary problem because we didn't have fast networks. This is really a core part of how we build apps and a core part of app architecture to be able to persist and use data offline when networks are not ideal. Why does it matter? How many people in this room use the MBTA? All right, that's all my Boston people. So I use the red line every day to get to work, and this is a typical picture I see every day on the red line, until you get to Park Street. As soon as the train stops at Park Street, people start looking around because basically everyone's gone. Their phones are chunking, bandwidth is limited, so everyone's competing, and you see people looking around confused. So if your app makes people do that, they're probably gone by the time Park Street is over. I call this the Boston MBTA red line use case. And then there's another use case that people like us probably don't see on a day-to-day basis. And this is a use case that I've encountered quite a bit in my journey with Kinvey, where a number of businesses are building apps for some interesting use cases. So this is actually a picture from one of our customers who built an iPad app for construction management. And so their users are people who are taking it on construction sites for extended periods of time, a day or two, with no networks. They have huge amounts of data because they're using iPads to represent all kinds of blueprints and maps. So there's a huge category of apps that need to support this kind of use case, which is the app actually gets used predominantly offline. And only in intermittent periods of time do apps come back online and synchronize with the cloud. And I've seen a number of these. There's use cases such as truck drivers or traveling salespeople who use mobile phones on the go and come back to their offices and then synchronize their data. And if you're like me, every time I travel to a foreign country, the first thing I do is shut off my data because I can't afford to pay for it. And so I'm also a user that runs into this use case all the time, and maybe some of you are as well. So there's really two categories. There's a category of use cases where you have very short periods of intermittent low networks, and there's a whole category of apps where you have extended periods with lots of data and requirement to sync it periodically. And we'll address both of these in our discussion today. So here's the gist of what we'll talk about today. I want to discuss some mechanisms to persist data on mobile and web. Disclaimer, I'm not a database expert, so this is not a database talk. If you ask me about SQL prepared statements or views or something deep, I might have to defer. But we'll talk about the landscape for mobile app developers. We'll talk about both kinds of use cases where you're storing pretty small amounts of data offline and also when you're storing enormous amounts of data. And then something that I really enjoy talking about and we've spent a lot of time trying to solve at Kinvey is data synchronization. How do you synchronize data between the apps and cloud in a way that's performant, in a way that's user-friendly? So we'll talk about some strategies. Things I won't cover, service workers, because we are primarily talking about app state and user data, not so much resources. And then asset caching and the cache API, mainly because I'm just not an expert in those. All right, so looking at the landscape, I thought I'll show it off as a Venn diagram. Starting from the web, maybe start from the bottom. These should be fairly familiar to most web developers. If you've built web apps, you have tools like LocalStorage, you have IndexedDB, just cookies, and a bunch of other things, but really it comes down to these fundamental concepts. And then on iOS and Android, there's things like user defaults, there's the keychain, Android has shared preferences, and there's a Venn diagram with a few things in the middle. So here's a pop quiz. Anyone want to tell me what goes in the middle? I have 3 native script queues. These were the last 3. So I thought I'll make a pop quiz for the last 3 items on the middle. Yes. You want to try this? All right, files. What? I have 2 more. SQLite. Excellent. And then one more, kind of, if you've been around in the last 3 or 4 years building native apps, you might have run across these guys. Anyone? So yeah, back when I started building apps for iOS, we were using file storage, and file storage was great. Our local storage looked like URLs and then the file responses for the URL, and that was adequate. And for a lot of apps, it's still adequate. So if you're using file storage, you have it across all mobile devices, and it works. And then the other two, SQLite has been around since forever. Most people know about it. And Realm's a relatively new technology, so I'll talk a little bit about Realm as well. But I've been pretty impressed using Realm. Let's talk about SQLite. I mean, SQLite is the big brother of all of these technologies, right? Since mobile came out, any developer who's built for mobile probably has encountered SQLite in some form. And it's ubiquitous. SQLite is self-contained, very reliable, fully featured, so you can do a lot of complex database things if you really put your effort into it. And a lot of people are familiar with SQL. So one of the big reasons for SQLite's popularity has been that using and querying it is very familiar to a lot of developers who've been around. The other reason it makes it really flexible is because naturally with SQL comes a massive ecosystem of tools and resources. But if you look at it, we don't have to go through this code all the way, but it's just a snippet of code to show off. If you were building with SQLite on iOS and Android, you'd probably be looking at code like this. And one of the challenges with this is not particularly mobile-friendly code. You're constructing large SQL statements to query. You are opening and closing databases. So one of the challenges with using SQLite since the beginning of mobile has been to find syntaxes and interfaces that are mobile-friendly to use SQLite. And a lot of people in the ecosystem have worked and made some really interesting things on top of it. And that's sort of one of the strengths of SQLite even today, which is I did a cursory GitHub search and I found 30,000 repositories for SQLite. And this means that there's just a wealth of resources. And if you're building either iOS, Android, or JavaScript for mobile, you'll probably find adapters for SQLite in the language of your choice. So over the years, I've used some of these. Core Data, which is Apple's iOS API for data persistence. Actually, you can persist with SQLite using Core Data as the interface. There's a bunch of Swift wrappers for SQLite. There's a bunch of object mapping libraries. We at Kinvey have used Object Mapper quite a bit, and we love it. The Android team at Google came up with a persistence library that I'm really impressed by. Because what it does is it allows you to have your Java or Kotlin objects annotated for SQL, which is really cool. So definitely would recommend looking at that if you're building for Android. And then for most JavaScript platforms like NativeScript and Cordova, there's SQLite adapters. And most of these offer you querying and database operations in a language that looks and feels more like JavaScript, not so much like SQL. So I think SQLite is still around and here to stay. If you find the right wrappers to solve your problems, I think SQLite is a perfectly great solution for mobile persistence. The other one that I want to talk about is Realm. So Realm was built about maybe 5 or 6 years ago by a team in Europe. And it's an open source platform. It's an open source database that works across a bunch of different mobile technologies. So they have a core C++ implementation and then wrappers for iOS, Android, Xamarin, and recently Node as well. Realm was essentially built as a better alternative to SQLite. So a lot of the limitations of SQLite are solved in Realm. Things like fast querying with interfaces that look very natural to the language that you're writing queries in. Transactional support with fairly lightweight syntax. The ability to receive notifications on objects, so your UI can refresh when objects change. Also, Realm provides a really rich set of object mapping capabilities similar to the stuff I talked about from Room. Realm also lets you write annotations for all of your objects. And finally, Realm comes built in with encryption. So If encryption is meaningful to you, this is quite powerful. So just a quick, what does a realm object look like? If you look at this, there's a few noticeable things. There's transactions, so you can create a transaction which creates an object. And if you look at the querying mechanism, this looks very natural. This is a very NoSQL style way of doing querying with a filter. So if you're using iOS or Android or Xamarin or even Node, Realm's a great alternative to do persistence on device. Well, let's turn our attention to the web. This again should be fairly familiar to web developers. This is basically the entire list of offline capabilities available in browsers. So there's file system, which is really not recommended anymore. Local storage and session storage, which web developers have used for a long time. Obviously cookies, WebSQL, which was deprecated a few years ago. And then IndexedDB and cloud storage. So IndexedDB is really the big player here. Local storage is as simple as it gets. It's a key value store. It's pretty straightforward to use. It only allows you about 5 megs of data storage across the major browsers. So if you're storing something very simple and quick and just need a read-write database, local storage is adequate for a lot of cases. The interesting thing about local storage is it will only hold strings. So if you're trying to store anything more complex like objects, you're probably going to be ending up serializing and deserializing them. And this starts to get pretty nasty when you're storing large amounts of objects, because very quickly you'll spend all your time serializing them. So it doesn't really scale great, but it's a perfectly adequate mechanism to store simple stuff. If you look at how the API looks, again, this is almost trivial. You set values for keys, and you can get them back. And if you have JSON, you'll probably use something like JSON.parse. The other big player in the web browser is IndexedDB. And IndexedDB is far more full-featured compared to local storage. It's optimized for storing large amounts of data, handles complex data really well, has pretty large storage limits. So typically, how much you can store on IndexedDB depends on the disk space available. Many browsers, it's like 50% of the disk space or something equivalent. So it scales up really well. And the other couple of things that make IndexedDB really peculiar are everything's asynchronous. So you receive DOM events on things that return from your requests. And everything's transactional. So pretty much every IndexedDB operation looks like a transaction. And I have a few examples. So a couple of things to note on IndexedDB. So first thing is you're registering listeners for error and success events. So this is what's going to get called once your DB request goes through. And within a database, you create what's called an object store. So IndexedDB works as an indexed table. So each index table is an object store. And like I said, IndexedDB goes with the concept of transactions. To do any kind of CRUD operation, you start by creating a DB transaction. Transactions obviously have types like read, write, or read, write. And then from your object store, you make requests. So again, this is the principle of asynchronicity that is pretty much universally true in all IndexedDB APIs. When you start thinking about more complex queries or retrieving more data, you get into the idea of using cursors. And a cursor is essentially like an iterator. So you open a cursor, and there's various ways of restricting how much data your cursor is actually iterating on by providing things like queries. And you're looping through a cursor by continuing, and the key and value of the cursor will give you the data that you need. So IndexedDB is a fairly robust, scalable way to store your data in the browser. And the nice thing about it is it's pretty much now a standard. So back in the day when I started developing for web and mobile apps together, we used to have adapters for IndexedDB, WebSQL, and LocalStorage. And on any browser, we would pretty much go through checking for which one was available. Because depending on what browser you wanted to run on, the available APIs were different. But now if you look at this horizontal, which is the current version of all the major browsers, pretty much universally IndexedDB is available, which is great. And IndexedDB isn't actually a database technology as much as it is an interface. So it's a interface definition that now they have revised to being a newer one. And most of the popular browsers have started implementing the new one as well. One thing about IndexedDB is, I don't know about you, but every time I look at the syntax, there's transactions and there's requests, and it all seems a little bit complicated. So a lot of people have taken different approaches to building stuff that makes IndexedDB easier to use. And if you're interested in persisting data on the web, I highly recommend looking at some of these options. DEXY essentially makes IndexedDB simpler. So the convoluted syntax of transactions and requests becomes a lot simpler with DEXY. LocalStorage is interesting. This is the kind of thing we did back in the day, which was it's a polyfill that looks at which database is available, and it will work with whichever one that it is. JSStore is something that basically makes IndexedDB look like SQL, which is not my personal preference, but it may be yours. And then PouchDB is another popular technology, but PouchDB essentially adds the whole CouchDB synchronization capabilities to IndexedDB. So if synchronization of data is something that's interesting, then PouchDB is worth looking at. One database technology that I've been really impressed by recently is LokiJS. So it's an interesting story. The maker of LokiJS, I think his name is Joe, has a really interesting talk on LokiJS.org that I'd highly recommend. And Loki was written also as a better alternative to SQLite. The principal difference is it's optimized for performance by using JSON as the storage mechanism. So it's an in-memory database, document-based, that uses JSON as its mechanism for persistence. And so the performance is really fast, NoSQL, in-memory, and in addition to being an in-memory database, they have adapters for all the popular database technologies out there. So LokiJS works with a number of different database technologies by having adapters. And by virtue of having adapters, it runs in a bunch of different ecosystems. It runs in Node, it runs in NativeScript. There's a NativeScript LokiJS adapter. There's Cordova as well. So I think this is one of the better alternatives for JavaScript developers who are building mobile to take a look at. And because LokiJS is entirely itself written in JavaScript and uses JSON, its entire interface as well as syntax for all popular things looks very similar to JavaScript developers to what they're used to. It also helps that all of their samples refer to Norse gods. So if you're into Norse mythology, apparently Loki is someone knows this, is what? Yeah, is the trickster. Loki is the god of mischief. So again, if you're into Norse mythology, you might appreciate the talk that the LokiJS creator has on his page. But what's really cool is this is all NoSQL and uses JSON-like syntax. So if you are familiar with, for example, Mongo's syntax, this should look familiar. There's a lot of similarity with typical NoSQL databases. And I mentioned that Loki was built for performance, so I found a quick test that someone in the community had written. And this is by no means a scientific, full-fledged performance test, so don't hold me accountable for that. But I found this interesting. This is basically inserting 1,000 documents into a database, and I tried looking at IndexedDB, Loki, and Pouch. So IndexedDB, if you guys can see this, took about 70 milliseconds. PouchDB takes roughly a long time, 4 seconds to insert the same number of items. And Loki takes about 6 milliseconds. So there's really a pretty remarkable improvement because of the in-memory database that they use and using JSON, basically. So this was basically the landscape of technologies available for persistence, but when we talk about offline capabilities and offline apps, there's a lot more to it than just using a database. There's basically your application code, and there's the persistence layer, and everything in between. And for some apps, it may make sense for the UI to directly just use persistence and call into the persistence layer directly, read and write data. But for most apps, it looks more like this. Everything in between is stuff like querying, figuring out online and offline policies, figuring out how we'll deal with writes on the device, and finally data synchronization, which is usually where the heavy lifting occurs. And in addition, most apps will persist eventually to some kind of backend store. We at Kinvey do all of the middle in blue. And so we've spent a lot of time trying to solve the problems in blue. So what I'm going to talk about for the last few minutes of this session is some of the common problems we've encountered while trying to solve these set of problems in blue, and what kind of mechanisms we've used to solve them. So to give you an example of what a Kinvey app looks like, we think about it in a much higher level of abstraction than the database. In Kinvey, you're dealing with what we call a data store and collections. So this basically is data store is an abstraction. Think about it as a store that you can read and write to and store data in. And a collection is the typical Mongo-style backend collection that's available for you to persist your data long term. So in this case, I have a collection called work orders and a local data store that I'm going to interact with. And I'll come to this sync in just a minute. Sorry. And as you would expect, on a store, you have things like pulling data from the backend, pushing data to the backend, synchronizing, running queries, things like this. The data store type is a way we came up with to manage your policies for reading and writing data from the backend. So we introduced data store types as a way to say, how do you want to interact with your data when you're offline? Do you want to keep it on the device? Do you want to go to the network first? Do you do offline first or network first? Do you do offline followed by network? These kinds of policies are all packaged into the data store types that we have. So in this case, the sync data store type tells me that I want to interact with my data while it's offline, and I'll decide when it goes back online. I'll decide when to synchronize. So once I create a store, I have a pull, to get data from the backend. I run some queries which look very much like a fluent syntax on JavaScript. I save some data, and then I sync. So at Kinvey, all of the heavy lifting that I talked about in this diagram is being done by the SDK. So one of the things in this code sample is saving the data offline, and this is one of the harder problems that most apps have to deal with. What happens when your users save data while they're offline? How do you synchronize that when they come back online? And so the way we approached it is, think about it as I have a backend store with a collection of data, and I've pulled it onto my device. What happens when the user now writes to the device while offline? So in our case, we create a queue where any write operations on the device get queued up as a reference. So this queue holds a reference to the row of data that changed. So the user could be offline for extended periods of time, and they may do a bunch of writes. And all we keep adding to the queue as a reference of what are the rows that changed. And eventually, we flush the queue when the user goes back online to synchronize it with the backend. And this, while simple for a few records, gets pretty complicated once you start talking about thousands of records. How do you manage asynchronicity? How do you manage things like batching? How do you keep it performant? And so we've spent a lot of time trying to figure out these problems and solve them in our SDKs. And this is basically things we've learned. Right? Sync is hard. How do you only retrieve changes from the backend that instead of retrieving all the data every time? So let's say I have a salesperson who's on the road using their mobile app. They come back to their office, connect to the Wi-Fi, and try to retrieve data. All I want to pull down is stuff that changed. I don't want to pull down everything again. It'll take forever. So how do you do that? So we implemented something called delta caching, which keeps track of a change set for every user that gets pulled down when they retrieve data from the backend. How do you do performance and scale? If you are syncing large amounts of data, think about how should I be batching this? Should I be putting it on background tasks or queues? How do you make sure that the app is responsive while data is being synchronized? And finally, I get asked about this a lot, is conflict resolution. Many people writing data offline, they all come back online, what happens? And so there's a whole set of conflict resolution policies that we offer in Kinvey. But in my experience, one tip about conflict resolution is that I've found that it's a lot better to resolve conflict resolution on backends and have devices be able to respond to failure to write rather than having many complex conflict resolution policies on device. That's been my experience, but I'm happy to talk about it in detail if someone has further questions, because conflict resolution is complex and there's a lot of nuance to how you implement it. But it's certainly something you need to think about. Finally, I wanted to just briefly mention a couple of APIs that are fairly useful. This is to detect whether you are online or offline. In iOS and Android, there's reachability APIs that correspond to these. These are browser APIs that will tell you if you're online. And the network information API basically tells you a bunch of stuff about your network, the bandwidth, the type of network like 3G or 4G or LTE. The one thing I read recently, actually, only last week, which was an interesting article about using network reachability, is it's a lot better to let requests fail before you look for reachability, because reachability APIs even today are fairly flaky. So you might get a reachability API telling you you're offline. Don't trust it. Make a request, and only when it fails should you actually be checking for reachability. This is an interesting article, and I think it makes sense, because ideally, you want your user to at least try and get data. You don't want to proactively prevent that. So these APIs are useful. The other shortcoming of the APIs here are they're not available across all browsers yet. So you may not be able to rely on them all the time. But they're still nice things to have in your toolkit. Everything I talked about in the last few minutes on Kinvey, as well as a number of these database wrappers, we've worked on, and all of our SDKs are open source. So if you're interested in learning more, contributing, or giving us feedback, please check out github.com/Kinvey. We have SDKs for pretty much every front-end technology out there, and we are happy to receive feedback and contributions. So if anything piques your interest, check out the GitHub repos and let us know what you think. All right, so here's what I'll leave you with. I think I tried to condense this into 3 or 4 things that I feel are important while building apps for rich offline experiences. Think of the level of abstraction you need. Do you need something that goes directly to the database, or are you looking for, is it suit your app to use a level of abstraction above it? So if you want direct database access, probably you want to use IndexedDB or SQLite. But a lot of options are available at abstraction levels higher, things that I discussed, or even things like Kinvey and Firebase and others. Think of the amount of data being consumed and persisted. The choices of database technology you rely on vastly differs based on the number of rows of data you're persisting. If you're building something that needs to be really performant and robust offline, you probably want to use the likes of a Realm or an IndexedDB. If you're building something that just needs to store a little bit of state offline, maybe you're better off with local storage. Your app's data synchronization policies will likely take up a lot of your time. Again, there are toolkits that help, and I showed you how we do it at Kinvey. But it's really important to think about data synchronization and policies that you'll use for online and offline. And finally, and this kind of is an obvious point, but platform support. So not every one of these technologies works across platforms. So sometimes the choice you'll make just depends on the platforms you want to support. That's all I have. The Kinvey team is here. Vinay works with me, and a couple of others are here as well. If you have further questions, feel free to reach out to one of them. If you have questions for me, I'm happy to take them. Yeah?
About conflict resolution.
Yeah.
Do you have like a real life example of how you guys dealt with that? Because I figure that like handling failure to write on the device makes sense, but it can be very frustrating for the user if it happens a lot.
Yeah, so that's a good question. We do have real life examples of conflict resolution, and like I said, they get pretty nuanced because the use case often dictates the solution. One of the things I've realized is, particularly at Kinvey, a lot of the customers we work with are persisting data effectively in a third-party system like a Salesforce or a SAP or a SQL Server, or even just Kinvey backend. And those backend systems already have business rules for conflict resolution because they may not even be building one type of client, they may be building many clients. And so one thing that I've recommended often is to have conflict resolution be part of the business logic on the backend. And we provide a way to write business logic on the backend. In our case, I believe last write wins is the default we use, but I've seen people change that. What really needs to be accounted for on the client, and this is part of our data synchronization, is when you have failures or when you have conflicts on the back end, what is the information that you pass back to the client to give the user a meaningful response? And that's really what it comes down to, in my opinion. Error handling on the client is what it comes down to. Effect. Yeah.
Yeah, maybe another note on just conflict resolution. Like that's been the biggest struggle for any sort of
Yeah.
that looks really slow.
Yeah.
Is there any opportunities that you know of to like use Couch with something more like an in-memory database? Because thankfully it's taking care of like the hard problem of
Yep.
saying,
Yeah, I mean, Couch, yeah, that's the value proposition of Couch. I don't have a lot of experience with Couch. I, I don't really know if there's a front-end technology that works with Couch on the back end. Does Couch have sort of interfaces that are easily understandable on the back-end side? Because
REST API.
if it's REST, then something like LokiJS or equivalent would work perfectly. I mean, um, probably you want to figure out how to write an adapter for LokiJS that persists to a mechanism of your choice on the client, and use Couch in the back.
You're not familiar already.
No, no, I am not. No, sorry. Yeah. All right, how are we doing with time? All right. I think that's all the time we have. I'll be around if anyone has questions outside. But thank you all for attending.